Hey, the project today is to make some wheels and pinions from raw material. I don't expect it to go perfectly, but I think I'm ready to try. So the watch that, or the movement that this is, I'm going to do this with is this Breguet Verge Fusil movement, which is missing the hour hand and the minute hand wheel. It did come with a cannon pinion that is missing some teeth that we'll see later, but those two wheels are completely missing. So it'll be fun to try to make them from scratch. Now, if you're watching this and going like that, it's crazy to make these gears. I totally agree. For one thing, I looked on eBay and you can see you can buy random Verge Fusil hour, minute hands, and cannon pinions in sets, and I should do that, but the whole point of learning watchmaking is to learn to make these things. But if you don't have a lathe and all these tools, then of course do that, and that's really the way 99% of watchmakers fix things anyway. Just to go back to how I'm going to try to do it, the lathes and the milling attachment and the gear cutting and the CNC index driver and all these other things are part of the problem, of course, that you have to solve to be able to do this, but you also have to have arbors and wax chucks and raw material and cutters. So I ended up, I just wanted to show you there's a couple of things. The wax chuck, the idea is that you take a piece of stock that's close to what you're going to make, like a gear blank. This is just a disc from AliExpress, a brass disc, but I'm calling it a gear blank. So you take that as a starting point, and then you glue it, super glue it to a chuck, and then you can cut it and work on it, and then remove the super glue using acetone. So I have a couple of wax chucks, plus you can also, if you don't have a wax chuck per se, you can just make it out of brass. So this is a kind of giant brass wax chuck. But I think the way I'm going to use this is I can make a wheel blank from a disc, but to make a wheel with the sleeve that's necessary to go around the cannon pinion for the hour hand gear or hour hand wheel, I'm just going to cut it out of this, and then this will end up getting shorter. But that way I can machine that. I can drill the center hole and machine the sleeve as part of that wheel. And then for the pinions, I have some steel raw stock, so that can just be trimmed down on the lathe and then slotted for the teeth. And for the cutters, I bought this huge box of random old wheel cutters that I just pulled pieces from. But I also have a topping tool, and the topping tool came with its own cutters. And I think that the most useful cutter is going to be this one from the topping tool. So we'll get into the topping tool in another video, but the topping tool, let's just to keep it simple, it has an attachment on the cutter that I'll remove, and then I'll just put the cutter on an arbor directly. And even though the cutter is only like 50% of the circle, it should work because you can do gears with a single little hob on a wheel. And so that's the plan for the tiniest slots. And then I do have some gear hobs for larger slots or gear teeth. Now, the other thing I can show is I bought this Verge Fusil as a reference, and you can see on this one has a different problem, which will be the subject of another video. But basically this one did have the wheels that we need. So the problem with this is that the center shaft broke. So the cannon pinion is stuck on the center shaft, but the cannon pinion's intact. The center shaft that's broken can be pushed out, and I can remake that shaft. So that actually would be a simpler repair than what we're going to do now. But just to show you, this is the gear or the wheel, hour hand wheel. Sorry, minute. This is the hour. Slips over the cannon pinion. And that's it. Those are the two things that we have to make. And when I was talking about the sleeve on the hour hand wheel, this is what I'm talking about. And then the pinion, this pinion is embedded in the wheel. So this wheel can be made flat and a hole can be drilled in it, and then the pinion part can be pushed into it and press fit. And then these guys, this is a kind of Breguet style case that this came with. So this was an intact watch when I bought it. It was broken in terms of that center shaft, but it was in this case. So this will get restored and put back in this case with a crystal fixed to it. But the point about this is that the way that these worked is that the movement hinges in and out here. So this will go back in this case with the dial, and the hinge is just a brass pin that goes through the hinge here. Holds that in. That's only relevant when you look at the movement and think about how it's all going to fit together for the one that we're actually working on. All right. So the thing that's crazy to me about this is that this is the gear or the wheel that I made, my first test wheel. It's not perfect, but I'm confident I can make wheels now. And this is the cannon pinion that I'm going to need to recreate. But this is a second or third wheel from a ETA movement. And it's so tiny that it's crazy. So I want you to see how tiny that is. So before I try to make these parts for the Verge Fusee, what I want to do is try to make the pinion part of this on the lathe and then slot those gear teeth in it. So this thing is, this pinion part of this wheel / pinion is 0.9 millimeter in diameter. And this little piece of metal is 0.9 millimeter in diameter. I'm hoping that this is white steel. It looks like it is. If it doesn't cut right, I'll try to find something else. But I didn't have any. My raw stock, I bought 2 millimeters and up. I really didn't expect to be doing things this small. But I'll try that. I'm going to try to make that pinion first, just as an exercise, because ultimately that's pretty much as small as it gets for hand making things. Most ETA move, of course, ETA, it's all made by robotics anyway. So there's no reason why you would ever need to make this. I just want to see. I like the idea of like working down at these scales that are like, okay, if you can do that, you can do anything. So that's the plan. Okay, so I tested the 0.9 millimeter steel rod, and I can't really deal with that because it's too short. So using a larger 4 millimeter and then bringing it down to 1 millimeter will give it much more stability on the and length, but stability on the collet side. So that's what I'm going to do. And then to figure out, to get my graver straight, I do like a long span sticking out. Now that's probably off by, it's not perfectly aligned, but basically there's an adjustment here on the angle of the cross slide like this. So I just got it as straight as I could. Oh. And I shouldn't be laughing because I like changed my eyewear to something not as safe and then that happened. Okay. But I can see that that thing is... So I want to go about the same again. Okay, so the problem is if I go too small, then I'm afraid the blade is gonna just whack that off again in the other the gear cutting blade will break it. So let's just try it like that. All right. So I just want to recap. I wear this smock to try to protect my clothing, but I still got some oil on this nice cotton shirt. So that's actually gonna... I thought this was like totally goofy, but it needs a top button actually. This is more of a lab coat for pharmaceutical or something. Doctor, not a clothes covering. So it doesn't have a button here. Okay, so I've got the workpiece in here. I don't really need to... This was set up for my other index driver here. But I don't really need... This works fine as a hand wheel. It's working, but I need to remove the cross slide because I'm not going to use that. This cross slide I bought for 65 Swiss francs, which is about 70 US dollars. And it wasn't made for this type of a lathe bed. It had an adapter for a larger lathe bed. So I had this piece made. I designed this in FreeCAD, and then I had it made by PCBWay in China for 35 bucks. And that's something that's in my video about the index driver. There's a little segment about that. Eventually I'm going to do a video about how to make... This is made out of stainless steel, so it's like super great part. Really cheap. If you don't have a big lathe, but you need to make parts, that's very helpful. So I have a separate graver rest. Just trying to remember which. I think that should work. The reason I say separate is because I used a graver rest base for the stepper motor for the index driver. But I bought a couple of these lathes. And then I just sharpened my gravers. Somebody's going to say, put the workpiece closer into the collet. So there you go. I want to take off 4 millimeters. It's about half of that. 5 would be half. 4 is basically exactly half. So I think I'll go a little bit further than half. I don't know about using cutting fluid on this. I think I'll try that. And then how I want to look, what I want to use for eye protection and magnification. And then have this micrometer ready for measuring. These are these vintage Zeiss. Oh, that's cool. So this is stereo, but it has a prism in there, so it fixes your interocular. So it's as if your eyes are much closer together, which makes the stereo better and less eye strain. Because the parallax. Okay, I think that'll do it. Okay, I'm going to call it. Going to call that ready. Okay, so now that I have the kind of raw stock prepared, I'm going to do some careful dimensions of this pinion that I'm going to try to copy. So I want to repeat again that I do not expect for this to work. First of all, I said this is from an ETA movement. I don't even know where it's from anymore. I compared it with ETA movements. I couldn't find one identical to this in the watch that I thought it came from. So I'm just going to try to copy it, just the pinion part, just to go through the motions, because again, this is the cannon pinion that we actually have to do. And it's massive, and it should be easier, right? So to do one, this is actually, so the actual dimension is 0.97. 0.97 millimeter is the maximum outer dimension of this pinion. So we'll just go and then the profile is kind of like 2 stages of getting smaller. And then on the underside, I'll measure all this. I just wanted to get a rough. So this is press fit in that wheel. Okay, so the profile looks like this. Wheel thickness, taper, then kind of rounded squarish. Now, this is a cool micrometer, Boley. And let's see if you can see that dial. I have a pocket watch with the same, made by the same manufacturer, Boley, Genève. So this, the way this works, it's spring-driven, hundredths of a millimeter, plus it goes up to 10 millimeters in hundredths. And it's nice and big display for the camera. So I'll see if I can measure this end to end. Wow. Okay, so that's 4.06 overall length. Okay, now I think let's just keep using this one because it's cool. Exercise. So to measure it to this point, that's so you kind of gotta leave it like that. Okay. So that's 2.365. 2.365. And that's to the bottom of the wheel. So we're going to phantom in the wheel here. That's to this side of the wheel. 2.365. The reason I put the 5 is because it's in between 2.36 and 2.37. It's closer to 2.37 though, so let's say 2.368. Now, the next thing I want to try to measure is the pinion, the geared part of the pinion. And that's 1.62. 1.622. 1.622, and that's to the bottom of the phantom part. Now we can measure the actual thickness of the wheel. .192. .192. I think that's everything needed to mathematically figure it out. Yeah. There's something I wanted to show you though before completing this micrometer thing. I found an even smaller wheel and pinion. Same kind of same overall structure. But that's, how big is that? 2 millimeters instead of 4. So that's like half as big. And I think that pinion only has 6 leaves. Let's see. Yeah, that's only 6. And I'll try to get a measurement on how large that is. And this is just for reference because this whole exercise is just to be like, what's the kind of smallest world that you could be in? These are all made robotically. There's no reason to try to make one by hand. That's a half a millimeter. A half a freaking millimeter. So I want to point out the tips of my micrometer are like a quarter of a millimeter. If I get this the right angle, the larger dimension, it's probably going to be 0.6, 0.58. 0.57. Okay. Anyway, you get the idea. That's pretty small. Okay, so that's all those dimensions. So I believe I'm ready to, this is just again to make the test pinion to see as a tolerance thing for me, like what happens when I get down into this scale, because I'm going to zoom back out and make something this big and it's going to be a lot easier. So it's fine if I fail with this. It's just that you'll see once I get onto that lathe how I'm going to try to accomplish these tolerances. And then when I zoom out to this larger size, I'll already have that kind of system in place for doing tolerances in the 100th of a millimeter or even 1,000th. And then it should make it easier when I get to this. Okay, so now I'm all set up with the stock that I prepared in the lathe. There's some issues with not being able to see everything, but basically that's the stock. And on the microscope view, you can see I have this micrometer zeroed on the, it's measuring the outer diameter of the portion of the raw stock or the workpiece that we're going to cut. And the reason I did that is I want to go once around and make sure that it's perfectly concentric, or check the tolerance. So I have this micrometer which measures in thousandths of a millimeter, doing that. And then I have this micrometer set to measure the distance that I move the blade into the workpiece. So I can turn this to contact the workpiece at its deepest point, and then using the math that I did over when I was measuring the piece I'm trying to copy, I figured out that the depth of the cut needs to be 0.265 millimeters. So I can calculate this. This goes up to 3 millimeters in hundredths, this micrometer. So 0.26 is nothing. I can figure out how I can zero it on the outer edge and then move it up 0.26, and then I'll repeatedly cut in this direction. So for right now, what I'm going to do is run my software. Is there any way to put this in camera without? This is my controller for my index driver, and I want to use it to step through all 8 positions and to watch the tolerance on this micrometer. So I'll move this out of the way because otherwise it'll get metal on it, shavings. But basically, just so it's on camera, I'm going to start the process by numlock on the keyboard and then press button B. I'm going to say 8 gear teeth because that's what we're doing this time. So that was the backlash reset. And then it's just going to ask me to type 1 through 8 as these, as each gear is cut. But we're not cutting anything right now. We're just going to step through. So the micrometer here, you can see it's at it's off by 2 1,000ths of a millimeter. If it was perfectly centered, it would be zeroed, but I'm not going to, well, I'll try to, it doesn't matter. The thing is, usually the first time it moves, it's going to find a position after some movement, and that'll be kind of a new zero. These guys, these little black tongs allow you to set some limits. So we'll set the limits at 15 1,000ths, 1.5 1/100ths. And that's just, you know, just to have some reference. And hit 1. It'll turn 1/8 of a turn. And you can watch that needle move it moved about 1/1000th. This guy. And then we'll do number 2. So you can see it moving to like minus. So you can see it move. Now it's at minus 4/1000ths. So now it's at minus 6/1000ths. Okay, so that's finished. The next thing is to try to get the depth of the cut correct. So I want to don't need this now. The depth of the cut needs to be 0.265 millimeters. So I need to figure out where 0 is. It's kind of good that well, it doesn't matter actually. This gear cutter is half. What is going on? Okay. That's a great view. Now, if that's our 0 position, I need to go through the full half circle though, because I think it gets tighter. Yeah, see, it's actually starting to cut right there. There's a couple of interesting things here. You can see it's pretty much correct center XY. But I also need to make sure everything's locked on the cross slide though. So cross slides have these little screws. Oh wait, do I want that locked yet? No, sorry. I want to lock that after I find the right position. And the right position is going to be this kind of touching position. So we'll go to the deepest side, which is here. Touch it. And then position this to measure the 0.265. So we want to go to 0 with this. And then turn this so the blade is not ramming into the workpiece. And then go forward 0.265. 0.5, 0.15, 0.2, 0.265. And then you're going to see when this turns around, it's going to hit it, right? Yeah. And it'll cut into it that deep. But we're going to be going back and forth like this on the cross slide, so it's not going to just ram into it. This axis is going to move back. But what I want to do now is lock this axis this direction so that that doesn't change, because that is the depth setting that I want. So now I should be able to back this off. If I refocus that, you should see that that's basically the depth of the cut. And everything else is locked. Back this off, and we're going to do it for real now. So 8. Okay. So now I'm going to go very slow with the motor. Very slow with the cross slide. Okay, you can hear it starting to cut. Okay, so I need to kind of inspect it while it's still on there. So it doesn't look that great in terms of the tips of those things. Now, is it because I didn't go deep enough? I think maybe that's the problem. Yeah, I think I didn't go deep enough because the edges of the gears didn't get the gear tooth shape. And the reason I'm looking at that now is because I can go again. I could go deeper, go again, but I have to figure out how much deeper to go. So here's a question. If we go back in, you know what, I can hold it next to the example. So in theory, I could use the topping tool to do this. I don't think the depth is that bad, but I could go deeper. I think I gotta go deeper. Okay, now what happened? Seems we had some slippage. In the positioning. Because I restarted the cutter. That's my only guess there. Or I went too fast and it just vibrated. But I think that's a fail. Hate to say it. It's too deep in the end. The gear tooth is not, it's not the right cutting wheel. That's the problem. But let's check, let's inspect. Seems like there was some rotation during the cutting. So I'll look at this under the microscope. Okay, so before I start, I'm going to go over this, but I wanted to mention, because I saw that my video from the flea market is on the screen there. There's two big flea market, or not flea markets, but actual watch markets coming up. So on the 3rd of November, if you're in Switzerland, on the 3rd of November, there's the Museum of Horology in La Chaux-de-Fonds. That should be all the info you need for that. That's a great one. That's in the basement of the Museum of Horology. I went last year. And then this one is in Geneva. I haven't been to this one, but I met somebody at the flea market in Plan Palais over the weekend who said that this is a big one. And it's on November 10th. So that's the weekend after. And that's the info. So I always hate it when people review things after the fact, which you kind of have to do, but don't let you know ahead of time that things are happening. All right, so about the problems with this, in the end, I used a topping tool cutter to do this, and I'll put this under the microscope in a second, but that's the fault, because it's made for cleaning up the gear teeth and the slot in the gear tooth, but it's not made for making gear teeth. So there are other types of cutters like this that actually have a gear profile. But let's see how we did. Let's look at it under the microscope and see how I did in terms of hitting my target for size. And then we can also look at some of the flaws. So the size target was 0.95. Let's see here. Sorry, 0.97. It's a little bit more than 1 millimeter. 1.05. That's 99. Oh, and then up here, well, that's beyond the point I would use. Anyway, a little bit too big, but I kind of knew that going into it because my raw material was not small enough. And I also had expected more. I'd expected the gear cutter to remove some material. So let's look at what the difference is between. I might need to stabilize this. Okay, so here you can see the profile of the cutter. And let me just compare that with, now this is larger, but this is a proper, see how this reaches, the larger one reaches beyond the tip of the tooth. Some of them even curve around and start to do the other inverse, but this one kind of peters out. It also looks uneven, but I think that's an optical illusion. Maybe not, though. Looks deeper on the left than the right. It also starts off, because it's a topping tool, it starts off thin like this, and then it changes, the profile changes as it goes, because it slices into a smaller, it wants to basically guide into an existing slot and then follow that slot around. Okay, so then just to see the profile of the teeth like that. So I have a couple of these gear cutters that I think, like this one, that I can use to do the pinion and the gears on the larger the wheels, the larger size wheels for the Verge Fusil. But I didn't have anything in this style small enough to do what I just did. I had previously made a larger pinion test, and this one I had a problem with the index driver not fully indexing the 8 equally, I think. No, this might have been a falling, this might have been a chuck coming out of the collet again. But anyway, this one, you can kind of see the problem when you don't have the completion of the top of the gear. This is what we saw with the smaller one also, is that the cutter has to be exactly the profile for the tooth, the angle, the curve, the depth, all of that. So there are like thousands of different cutters. Well, I don't know about thousands, but you know, infinite number of different cutters for an infinite number of different gear profiles. I also want to show the difference in size of these two. This is the first one I did, and then this is the one that I tried today. And when I bought my cutting tools, that pack of the cigar box of tools at the beginning, this was in there. So it was probably something from a hobbyist also, and this was their attempt at making a cannon pinion. But look at how big theirs is. And it also feels like here they ran into some similar problems in terms of twisting of the teeth. Different depths, you know. This almost feels like it was made with, not even with a, it was made the same way, except for these teeth are very weird. But that's no matter. The point is, this also made me, just seeing that, who knows, that could have been a very early student. But, you know, this stuff's not easy. And the reason I'm going for this really tiny size is just to find out how not easy it is. And this was, again, the pinion size that I was kind of trying to copy. And you can see that size difference. Okay, next thing. Oh, I know the other thing I wanted to mention was you can, I thought when I did this, I would just slot the whole thing and then use the lathe to bring it down, you know, because there's a whole shape to this that I didn't do. But I realized, for one thing, I don't want to waste the time doing it on this one, but it's basically, I don't want to try to cut it down on the lathe afterwards. I think the key would be to get the whole profile figured out first. At least on, you might, I mean, I'm not going to go down to the pivots, but I'm going to go down to the point where I'm not machining over the teeth again. So the problem with that is you get down to like a 0.5 or 0.4 millimeter shaft that you're then machining the pinion out of. There may be some compromise, but basically I don't want to be trying to take down the thread, because the lathe is going to be like chunk, 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 chunk. Somebody may know something about that. Like, you shouldn't do that. But my instinct is to try to do as much of that first as possible. And then I wanted to point out that on my website, and this will be updated with new information as it gets better. But basically I have the whole project for the index drivers here. And then this is a project you can make yourself. You make the index driver yourself, and I wrote the software for it. So the software is here to be downloaded, and then there's links to all the parts that you need. But this is going to be changing because I discovered that my Z-axis flexible coupler is a little bit too not stiff enough on the rotation. So I ordered a couple of different versions of that to try. And then I also need to get better braking on the stepper motor. So I ordered some brakes for that. So that'll get updated with those improvements. But then also, if you go to shop for these cutters, if you click on the shop tab and then you go down to cutting tools, you'll get to these are Swiss vendors for cutting tools, Louis Bellet and Glore. And Louis Bellet has them in stock. So these are cutters that the wheel is built into shank, and then you just order. Everyone is different. So you can order a shank size that fits in a standard collet for your lathe, whether it's a W12 or a B8, and then you order exactly the module and the cutter that you need. Module meaning the depth of the tooth cut or whatever. We'll get into that in the next video. So that gets me to another point, is that there's going to be a follow-up video where I'm going to do all the math for the wheels that I actually have to make, that this video I was getting at, but I'm running out of time because it's been over an hour. I'm going to do all the math in the other video, figure out exactly what those cutters need to be, and then try to order or get the proper cutters from one of these vendors. And that'll be the second video, and then I should be able to do this. So I think that's it. I'm sure I'll think of something else I forgot. Feel free to ask questions, and I'll eventually finish this project, and then I'll be in a whole different world. All right. Thanks for watching.